Welcome to the third module on Introduction to Scientific Programming. In this module, we're going to deal with the issue of data wrangling, essentially using an exercise to explore methods of data wrangling, which is essentially the good practices associated with storing and manipulating data. We're going to use a case study that integrates three different data sets: US Census data, a CDC public use dataset on Lyme disease, and the PRISM dataset, which contains commonly used climate variables. In the RMD file that we've provided to you to help you get started, you'll notice that we use several libraries, including the tidyverse library, which contains the package readr. We're going to use that package in order to read comma-separated value files or CSV files in, and the function that we will use is read_CSV, which may be slightly different to the read.csv function you're used to if you've taken any other introductory classes in R. In the module that follows this one, you're going to have the option to save the data that you've wrangled into shape, either as a CSV file or as an object in R. For completeness, we explain here how you can save a data frame that you've created and load it in later. What we're striving for in this module is to create a data frame that's in the tidy data format. Each variable should have its own column, each observation should have its own row, and each value should be in its own cell. In order to achieve that today, we're going to use a few commands from the dplyr package. In particular, the functions gather, select, and mutate. We'll additionally learn to do some string manipulation. This is to help us when data is typed inconsistently either within a data set or across different data sets, and is a common obstacle that we have to overcome. In order to do this, we'll use the stringr package, and in particular a function str replace all. We'll also use the paste command, which is part of the base R package. This module works with georeferenced data, particularly at the county level in the United States. Counties in the US are often referenced by FIPS codes, which are similar to zip codes. In the examples we see here, California has a FIPS code of 6, and Orange County in California has a FIPS code of 59. Together, the full FIPS code is 6059 because the county component is potentially a 3-digit number, which is why we pad it with a 0. You see another example of Clark County here in Georgia, which has FIPS code 13059. So the FIPS code can be in total either 4 characters long or 5 characters long. This module will also introduce us to piping, which is a method of coding that improves readability so that when we come back to our code or we share it with our colleagues, it makes more intuitive sense. We see in these three examples that we ultimately achieve the same goal in 3 different ways. The first example relies heavily on writing different functions, which are executed one after another. The second example nests functions together, the problem being that ultimately the verb that is executed last actually appears first in the code. The final example, which is piping, takes our actor, Fufu, has it hop through a forest, then scoop up field mouse, and then bop it on the head. In this simple example of piping, we first assign the number 2 to x, then we take the sign of that and the square root of that and assign it to y, which becomes a number beginning 0.95. In the lower part of this slide, we do exactly the same thing, except we just keep overwriting x. So first it takes the value 2, and then it gets rewritten to be the square root of the sign of what it was originally, again resulting in the same number, 0.95. To achieve the same thing using piping, we would first use the library magrittr, then assign the number 2 to x as before. However, this time we take x, we pass it over to the function sign, and pass that over to the function square root, and assign the whole thing to y, again resulting in this number beginning 0.95. If we're happy to keep overwriting our variable x, we would first assign it so that it has the value 2, and then we use the percent signs which inside have a less than and greater than sign back to back, so that we're taking x, passing it over to the left so that it goes through sign and square root, and then passing it back to be x again. This time again resulting in the number 0.95. Also relevant to this module is the idea of applying a function to each row of a data frame. We're going to illustrate this with a little example where we create a simple data frame called a tibble, which is called pocket money. And inside pocket money, we have the characters Jack and Jill. They have money in their savings account, $10 for Jack, $15 for Jill. And they have the money they've just earned from doing their chores, $5 and $2 respectively. Next, we create a function called getSum, which takes the savings and the chores and does what you might expect, adds them together. We're going to implement this function by starting with our data frame, pocket money, passing it through the pipe, and telling R to do this calculation row-wise, row by row. The calculation creates a new column, total, using the mutate verb, and total is simply the application of the function getSum. So we see when we print out the data frame, we've created a new column total, which is the sum of the savings they already had and the money they recently got from their chores. If we do the same thing, but omit the step row-wise, we see that we get a very different answer. Now the function takes all the money that was in both of their savings and all the money that they would have got from their chores and adds it all together to get $32 and assigns that to each of the individuals. And we see that that's going to create a problem in Jack and Jill's household. At the beginning of this presentation, I stated that we're going to work with 3 different sources of data. And so one of the things we will have to do is combine those together. In base R, the function that is typically used is the merge function. In the dplyr and tidyverse version of R, we use join functions. I've presented some links here that allow you to read a bit more about them, and also some examples using superheroes that show you the different ways in which you can join data together. Importantly, there has to be at least one column name in common between the 2 data sets you're joining, and if you don't specify column names, R will typically do a natural join using all the variables that are in common between the 2 data sets. We'll illustrate 2 different joins with a simple example here. First, we'll do a full join and look at the results, and on the next slide we'll do an inner join and look at those results. In order to do this, I've created 2 simple data frames. The first is called Gourmet, which takes 4 different states and their characteristic barbecue sauce. I then make another data frame with 4 states and their characteristic greetings. And we see that when we do a full join on gourmet and greetings, we actually create 5 rows because we actually have 5 different states. They're not all the same states in the 2 different data frames. When one of the states, for example, North Carolina, has a source but not a greeting, we see that an NA appears in the greeting or the word column. Similarly, New York has a word for a greeting but doesn't have a barbecue sauce. Using the same 2 data frames, if we instead do an inner join, we now see that we retain only the 3 states that have both a characteristic barbecue sauce and a greeting. The last key part of wrangling that we'd like to introduce in this presentation is about obtaining summary information from data frames, and in particular, the idea that we can group rows of data together and perform functions on them which would allow us to inspect, for example, average quantities. In this example, we've created a data frame called grades that has 4 columns. Students, identified by a number, their major, E or B, for example, ecology or biology, a UG designation for whether they're undergraduates or graduates, and their test scores written out as a percentage. Now we can take the data frame grades, pass it through a pipe to the function groupBy, where we supply, in this case, the argument major. We then pass the result of that through a pipe and call the function summarize, where we create a new column, avScore, which is simply the mean value of score. We see the net result then is a much more condensed data frame that has grouped all the students into whether they are biology or ecology majors and averaged their test scores. We'd now like you to begin work on the wrangling module by navigating to ELC and going to the wrangling folder. There you'll find a wrangling RMD file, and note that you'll also need to download some files from the data files part of this ELC workshop. Once you have the RMD file on the RStudio server, you can begin to work through the step-by-step instructions, and if you have any questions, contact an instructor.